One of the most astonishing frontiers in modern science is the ability to manipulate and engineer matter at the scale of a single atom. While atoms were once thought of as the ultimate limit of precision, today researchers can isolate, position, and even control the function of individual atoms. This opens doors to technologies with unprecedented miniaturization, sensitivity, and performance, paving the way for a new generation of materials, devices, and computing systems that operate at the quantum level. Why focus on a single atom? Because atoms are the building blocks of everything, and controlling a single one means mastering matter at its most fundamental scale. When only one atom is involved, quantum effects dominate, leading to behaviors like discrete energy levels, tunneling, and spin-based phenomena. This allows researchers to exploit properties that do not exist in bulk materials. For example, a single atom of phosphorus implanted in silicon can act as a quantum bit, qubit, storing and processing information in ways classical computers cannot. So what can we actually do with single atoms right now? One of the most active areas is quantum computing. Companies and labs are racing to build stable qubits using single atoms, such as trapped ions, neutral atoms in optical lattices, or electron spins bound to single defects like nitrogen vacancy centers in diamond. These atoms can be precisely manipulated with lasers and magnetic fields to perform quantum operations. Another breakthrough field is single-atom catalysis, where individual atoms of metals like platinum, gold, or iron are anchored onto a support material and used as ultra-efficient catalytic sites. Because every atom is active, the process is not only more economical, but also more selective and environmentally friendly. Could a single atom really power future devices? In some cases, yes. Experiments have demonstrated single-atom transistors, where the flow of electrons is controlled by a lone atom acting as a switch. These devices offer extreme sensitivity and are being explored for ultra-low-power electronics or next-generation sensors. Similarly, single-atom magnetic storage has been achieved by placing magnetic atoms, like holmium, on a substrate and writing information based on their spin state. This could potentially allow data storage thousands of times denser than today's hard drives. What about the future? Future technologies will likely combine atomic-scale engineering with machine learning, AI, and real-time control systems. We may see quantum networks where single atoms transmit entangled photons over long distances for secure communication, or biocompatible single-atom sensors that detect disease markers or chemical signatures inside living cells. Advanced imaging methods like scanning tunneling microscopy, STM, already allow scientists to move individual atoms to construct custom molecules or circuits, atom by atom, which could lead to a new era of programmable matter. Is it really practical? There are challenges. Working at this scale requires extremely controlled environments, ultra-high vacuum, low temperatures, and high stability to prevent thermal or mechanical noise from disturbing the system. However, steady progress in nanofabrication, cryogenics, and quantum control is rapidly making single-atom technologies more reliable and scalable. In fact, we are likely entering an era where entire devices can be built from the bottom up using just a few atoms arranged with atomic precision. So when we speak of single-atom technologies, we are really envisioning a future where the line between matter and machine blurs, where each atom is not just a passive component, but an active element of information, energy, and function. The smallest unit of matter may soon become the most powerful tool in engineering. Single-atom transistors use an individual dopant atom, commonly phosphorus in silicon, as the active channel between source and drain electrodes. Coulomb blockade effects at cryogenic temperatures allow precise control of electron transport through the atom's discrete energy levels. Gate voltage tuned the atom's ionization state, switching the transistor on or off with minimal leakage current. Atomistic fabrication uses scanning tunneling microscopy, STM, to position dopants with sub-nanometer accuracy. These devices demonstrate the ultimate scaling limit of classical electronics. A phosphorescent silicon transistor operating at 100 mK showed discrete conductance steps corresponding to single electron tunneling. It's like controlling water flow through a single faucet valve rather than an entire pipe network. Isolated atoms or ions trapped in electromagnetic fields serve as qubits, with quantum states encoded in their electronic or hyperfine levels. Laser pulses implement high-fidelity quantum gates by driving coherent transitions between these states. Long coherence times, exceeding seconds, arise from the atom's insensitivity to environmental noise when properly shielded. Scalable architectures link multiple single-atom qubits via photonic interconnects or phonon-mediate interactions in ion chains. These systems form the backbone of leading quantum computer prototypes, a chain of 6 ytterbium ions performed entangling operations with greater than 99% fidelity in a surface trap. It's like using single, perfectly tuned piano keys to perform complex chord progressions without any disk. Atomic scale memory exploits the ability to switch an individual atom between two stable configurations, such as adsorption sites on a surface, to encode bits. Spin-polarized STM tips can write and read these states non-destructively by sensing local magnetic or electronic signatures. Thermal stability at cryogenic temperatures ensures data retention for hours or longer. Arrays of such bits have demonstrated packing densities above 1 terabit per square inch. This approach pushes storage beyond the limits of conventional flash memory. 8 holmium atoms placed on a magnesium oxide film stored 1 byte of information via their magnetic moment orientations. It's like engraving a single letter onto a grain of sand and then reading it back with a microscope. Single atoms dispersed on supports act as highly efficient catalysts, offering maximal active site utilization and unique reaction pathways unavailable to nanoparticles. Quantum confinement and strong metal support interactions modify the atom's electronic structure, lowering activation barriers for targeted reactions. These catalysts demonstrate exceptional turnover frequencies for processes like CO oxidation and hydrogen evolution. Stability under reaction conditions is achieved by anchoring atoms at specific defect sites or within coordination cages. Single-atom catalysis thus promises greener, more selective chemical production. Platinum single atoms on graphene achieved a CO oxidation rate 10 times higher per atom than platinum nanoparticles. It's like using one expert craftsman instead of a workshop of apprentices to achieve superior quality and efficiency. Single magnetic atoms on insulating substrates can maintain stable spin orientations at low temperatures, functioning as nanometer-scale magnetic bits. Spin excitation spectroscopy with STM reveals spin flip energies and magnetic anisotropy barriers, key parameters for data stability. Readout is performed via inelastic electron tunneling signals that change when the atom's spin flips. Writing involves applying local magnetic or electric field pulses to reverse the spin state. This technique points toward ultra-high-density magnetic storage media. A single iron atom on a magnesium oxide surface exhibited a magnetic bistability lifetime of over 30 seconds at 0.5 K. It's like flipping a tiny compass needle on a leaf and reading its direction with a magnifying glass. Isolated atoms or color centers in crystals serve as single photon sources emitting 1 photon per excitation cycle, essential for quantum communication. Emission lengths can approach the atomic natural width, enabling indistinguishable photons for interference protocols. Positioning atoms in photonic nanostructures enhances emission rates via the Purcell effect. Resonant excitation allows triggerable, on-demand photon generation at telecommunication wavelength. Such emitters underpin secure quantum key distribution networks. A single erbium ion in a silicon photonic cavity emitted 10,000 triggered photons per second at 1.5 mils. It's like having a lone street lamp that flashes one perfect beam of light exactly when you press a button. Individual atoms or ions near a surface can detect minute changes in electric or magnetic fields through energy level shifts, Stark or Zeeman effects. Scanning probe microscopes, functionalized with a single atom, achieve subnanometer spatial resolution in mapping surface potentials. These sensors measure single electron charges, local spin states, or nanotesla level magnetic fields. Integration with cryogenic circuits yields ultra-sensitive detection of quantum phenomena. Single-atom sensors thus open windows into nanoscale environments. A chromium atom on an STM tip resolved single-molecule charge states by detecting local electric field variations. It's like placing a single feather at the end of a rod to feel the slightest breeze in a still room. Theory predicts that a single atom in a harmonic trap coupled to hot and cold reservoirs can function as a quantum heat engine, converting thermal energy into work at the single particle level. Work strokes are implemented by modulating the trap frequency, while thermalization steps exchange energy with engineered reservoirs, e.g. laser-cooled ions. Efficiency and power output follow quantum thermodynamic relations that differ from classical engines. Experimental realizations with trapped ions have demonstrated stochastic engine cycles and measured work fluctuations. These platforms probe the fundamental limits of thermodynamics in the quantum regime. A single trapped ion heat engine achieved 30% of the Carnot efficiency over hundreds of cycles, with millisecond cycle times. It's like running a steam engine with a single water molecule, watching it push a microscopic piston back and forth. Combining the above single-atom technologies promises integrated devices, for instance a qubit C-coupled single-atom sensor that performs quantum error-corrected measurements, or a single-atom catalyst on a photonic chip for on-chip chemical analysis. Advances in fabrication, control, and packaging aim to unify atom-scale electronics, photonics, and mechanics. Hybrid systems may include single-atom memories interfaced with quantum communication channels or sensors driving feedback into self-healing materials. Realizing such multifunctional atomic platforms will require coordinating atomic manipulation, coherent control, and scalable architectures. These future devices could transform computing, sensing, and energy conversion at the ultimate limit of miniaturization. A proposed device integrates a single atom transistor and qubit in the same silicon site, enabling quantum logic operations with in-situ readout. It's like building an entire smartwatch on the head of a pin, where each component is a single atom performing a unique function.